Alright, so in this video, I'm going to be solving the problem 2 to the power of 101 minus 2 to the power of 100. So to solve this problem, I'm going to first start by rewriting 2 to the power of 101 as 2 to the power of 100 plus 1. Now, the reason I did that is because now I can use this property that states that if I have something in the form a to the power of m plus n, this is equal to a to the power of m times a to the power of n. So 2 to the power of 100 plus 1 is going to equal 2 to the power of 100 times 2 to the power of 1. And now I have this minus 2 to the power of 100. Now from here, I can factor out 2 to the power of 100. So I get 2 to the power of 100 times 2 to the power of 1 minus 1. Now 2 to the power of 1 is equal to 2, and 2 minus 1 is 1, so I'm left with 2 to the power of 100 times 1, which is equal to 2 to the power of 100. Now, there is actually another method of solving this problem. So going back to the problem, I have 2 to the power of 101 minus 2 to the power of 100. Now, before I rewrote 101 as 100 plus 1, but how about I rewrite 100 as 101 minus 1? So now I get 2 to the power of 101 minus 2 to the power of 101 minus 1. And this is the same thing as 2 to the power of 101 minus 2 to the power of 101 plus negative 1. Now, if I use that property again, that states that a to the power of m plus n is equal to a to the power of m times a to the power of n, I get 2 to the power of 101 minus 2 to the power of 101 times 2 to the power of negative 1. And now if I factor out 2 to the power of 101, I get 2 to the power of 101 times 1 minus 2 to the power of negative 1, which is equal to 2 to the power of 101 times 1/2, which is equal to 2 to the power of 101 times 2 to the power of negative 1, which is equal to 2 to the power of 100. So that's the second method of solving this problem. Alright, so in this video, I'm going to solve the equation 1 to the power of x is equal to 2. So, before we even start solving this, if, let's say, x is equal to 1, then I have 1 to the power of 1, which is equal to 1. And if x is equal to 2, then I have 1 to the power of 2, which is also equal to 1. And you can go even 1 to the power of 10 is still equal to 1. So you may be thinking, what possible value of x can make 1 to the power of x equal to 2? So let's try solving this. What I'm first going to do is start by taking ln of both sides. So I get ln of 1 to the power of x is equal to ln of 2. And ln is the same thing as the natural log. And the reason I took the ln on both sides is because it comes with a property that states that if I have something in the form ln a to the power of b, I can move this exponent b to the front, so this turns into b times ln a. So in this case, I have ln 1 to the power of x, and I can move x to the front. So I get x times ln 1 is equal to ln 2. And you may be thinking, we could just divide both sides by ln 1, and x would equal ln 2 over ln 1. However, the only problem with this is that ln 1 is equal to 0. And remember, anything divided by 0 is undefined, so this would be undefined. So we know that this equation has no real solution, but it could still have imaginary solutions. So to actually solve this, I'm going to use something known as Euler's formula. And basically what this formula is if I have something in the form e to the power of I times theta, this is equal to cosine of theta plus I times sine of theta. And I know to many of you watching this video, this may just sound like a bunch of gibberish, but just hang on. So let's say that theta is equal to 0, right? Say that theta equals 0. So now I get e to the power of I times 0 is equal to cosine of 0 plus I times sine of 0. Cosine of 0 is 1 and sine of 0 is 0. So I get this all is equal to 1. Now, what if we say theta is equal to 2k pi? And k is just a substitution for all real numbers. So now I get e to the power of I times 2k pi is equal to 1. Because all we did was we just substituted theta in for 2k pi into this same thing. So now, because this is equal to 1, we can remember our first equation, which we started with 1 to the power of x equals 2, we can substitute in this for 1, meaning I get e to the power of I times 2k pi to the power of x is equal to 2. So just think of this as 1. So I basically 1 to the power of x equals 2. And now with this, I'm going to take the ln or natural log on both sides. So I have ln e to the power of I times 2k pi to the power of x is equal to 2. So I'm going to now bring this x down using property of natural logarithms. So I get x times ln e to the power of I times 2k pi is equal to 2. Is equal to ln of 2. Because if you take ln on one side, you have to do the other side. And now I can also move I times 2k pi to the front. So I have I times 2k pi times x times ln e is equal to ln 2. ln e is simply equal to 1. So I get x is equal to ln 2 over I times 2k pi. And now I'm going to multiply this by I over I. So I get x is equal to negative I times ln 2 over 2k pi, because I squared is negative 1. So this is my solution.